Okay, in section 2.5, which covers implicit differentiation, they want to know, in problem number 27, says to find dy over dx by implicit differentiation and evaluate the derivative at the given point. So, the implicit equation that is given in number 27 is tangent of x plus y equal to x, and they want to find the derivative dy over dx at a point x equal to 0 and y equal to 0. I usually write down this little at symbol to let me know that once I do find dy over dx over here, I'm going to evaluate it for one particular value, right? So I might, draw a little separation here to let me know that this is in the general case, and this is on the right here going to be a specific value that I am finding. So, one little side note, maybe I'll write down here, and I know that the tangent of any function, if I take the derivative with respect to x of the tangent of u, it's going to be equal to the secant squared of u times the derivative of whatever u is with respect to x. So the derivative of tangent of x plus y, I will allow x plus y to be the inner function here for my application of the chain rule. And so the derivative of tangent of x plus y is going to be secant squared of x plus y times the derivative of x plus y with respect to x. Well, derivative of x is just 1. Derivative of y is, we don't know, so we leave a little placeholder there, dy over dx. And little funky grouping symbols there. Erase that a little bit. There we go. Okay. And if we take the derivative of the left-hand side, we also have to take the derivative of the right-hand side, and the derivative of x is just 1. Okay, so let's see, what can we do? Well, we can choose to, we want to get this dy over dx by itself. And there's no other dy over dx's here, there's no dy over dx's out there, so maybe one thing that we could do, we could distribute this first, right, and then solve for dy over dx, or we can divide both sides by secant squared of x plus y. Let's try that out. If we divide both sides by secant squared of x plus y, because in this factor there's no occurrences of dy over dx. Remember that we're trying to solve for dy over dx first here. So since we're trying to solve for this and it doesn't occur in this other factor, we can divide both sides by it. 1 plus dy over dx equals 1 over secant squared of x plus y, and that's it. And then we subtract by 1. Also notice that 1 over secant is the same thing as cosine, right? So this is going to be equal to cosine squared of x plus y minus 1, and that means that this is dy over dx is equal to this. The other thing that we also know maybe is that this is the same thing as negative sine squared of x plus y. These two things are pretty simple. This comes from 1 minus cosine squared of x plus y. 1 minus cosine squared of anything is going to be sine squared of that, so cosine squared minus 1 will be negative sine squared of x plus y. Okay, so this is the general case. This is what dy over dx is equal to. In general, for any value of x plus y, for a specific value of x plus y of 0 and 0 for x and y, then dy over dx will be equal to negative sine squared of 0 plus 0, which is just sine squared of 0, which is just 0. And that should be the answer to number 27. The next problem, number 29, the Witch of Agnesi. Let's actually move this down here so I have a little bit more room to work. So, press the digit auto magically, it happens, right? And let's see. Okay, so they are asking the same question as before, only they give you a pretty picture at the same time. So if you look at the pretty picture, they want to know what the derivative at this one particular point, 2, 1 is. And in the picture, they highlight it for you. One of the first things that I do to try and figure out whether or not I'm going to be correct about something or not is I try to graphically look at this and try to determine the sign and magnitude of my derivative. So if I try to draw a tangent line through this, I might get something that looks maybe a little bit like this. Okay, so one of the things that I notice right away is that it is probably going to be a negative slope of the tangent line, and it's probably going to be pretty small in magnitude. And this will let me verify my answer and give me a touchy-feely at the end to let me know that maybe I am correct without having to check in the back of the book. So, okay, enough of touchy-feely graphical intuition. Let's actually find what dy over dx is equal to according to implicit differentiation. So, I take the implicit derivative of the left-hand side. I could use product rule here with this and this. One thing that I'm probably going to do right now is avoid overcomplication by just distributing this y to both terms. So this gives me x squared y plus 4y equals 8. Okay? So now I'm going to take the derivative of this. So this is just going to be, let's do the easy one first. Let's do the derivative of 4y, because I would just take the derivative of both of these two terms separately and add them together anyway. So I'm just going to do the second one first here because it's pretty easy. The derivative of 4y, I don't know what the derivative of y is, so I use a placeholder of dy over dx. Derivative of 4 times y is going to be the same thing as 4 times the derivative of y. A derivative of y we're leaving as a symbol, dy over dx. Okay, so that's that term. Then the second term we are going to add. Now we have to use the product rule. We have x squared as my first function, and my second function is this unknown function y. So I hold one constant and then take the derivative of the other. So I'll hold x squared constant and multiply it by the derivative of y. And then I have to add to that. I took the derivative of y. This time I'll take the derivative of x squared with respect to x, so that becomes 2x, and we hold y constant. All right. So then on the right-hand side, the derivative of 8 is just 0. Okay, so now I have these two terms right here that both have a dy over dx in them. I'll send the other two to the other side. So this gives me negative x. Oh, no, I'm sorry, not the other two. The other one. This is just one. Is multiplication. Right? So that's just 2xy, negative 2xy, because I subtract it from both sides. And this is going to be equal to, I can factor out a dy over dx in both terms that are on this side. And that's going to be 4 plus x squared. And then I will divide both sides by 4 plus x squared. So I get dy over dx is going to be equal to negative 2xy over 4 plus x squared. And we're supposed to evaluate this at a point 2, 1, x equal to 2. So at 2, 1, one specific instance of this general derivative, exactly the derivative at this point, dy over dx will be equal to negative 2 times 2 times 1 over 4 plus 2 squared equal to, let's see, this is negative 4 over 8 equals negative 1/2. Okay, it's negative and small in magnitude. Well, I would consider this. Anything less than 1 is probably what I would consider, at least at this scale, small in magnitude. So I got pretty good touchy-feely about this. So if you check in the back of the book, it gives you a very unceremonious negative 1/2. So it matches what we found, and that's number 29. Okay, so and then we did what? We did number 27 and 29. Next time, in our next video, we'll do another 2 out of section 2.5.